All right. So I have another 40 minutes before you are allowed to enjoy your weekend. I think you definitely need it. And so now I'm going to, well, you know, I'm not solving things. I'm giving you ingredients that ultimately should enter this whole business of AGN feedback, okay? And so ultimately now I'm coming down to the disk, the accretion disk, and I'm telling you that, there's a lot of dynamics in the accretion disk. And because I think there are a few people doing seismological stuff, maybe, I don't know. Were there? Helioseismology or anybody? No? Yes, there you go. So, I'm going to give a helioseismology or a magnetoseismology approach to that thing, okay? And what is that? In a nutshell, it is if you have a given equilibrium, okay, tell me all the waves and instabilities that are accessible to that equilibrium. That was actually first done for fusion plasmas where, you know, you have a toroidally complex configuration. You know that the equilibrium there is given by pressure gradient balanced by Lorentz force. In fact, that is the basic Grad-Shafranov equilibrium for a configuration. And it has given an enormous amount of information about the various ways in which, if you are happy with an ideal MHD description of the plasma, this plasma can shake and become unstable. And it is the magnetohydrodynamic analog of helioseismology. Okay, helioseismology, in a nutshell, what does helioseismology do? If you have a run of the temperature with depth, and you're happy with just assuming that your star is nice, spherically symmetric, then that's all you need, just like density as a function of radius. And then the fact that then typically you would have your, if the temperature increases, also the sound speed changes. And so you would have a possibility for, what are the eigenmodes? The eigenmodes are those that fit the ball, all right? So you have sound waves, for instance, that are reflected at the surface because they are all of a sudden, they hit a giant discontinuity. But they are refracted deep down in the interior because there, well, if you go deeper, this part of the wavefront travels faster, and so you refract. And if you then do this and you can fit nicely in the sphere, then you're an eigenmode. That's the forward spectral problem. And if you do that, then helioseismology obviously has come the backward spectral problem. So you have also observations that give you observed frequencies versus horizontal wavelengths, basically. And these are the 5-minute oscillations of the sun, all right? And there are these ridges, and these ridges are also what you get if you do analytic theory for this. And in fact, combining this information, observations, and interior run of radial temperature structure, you can do sort of an iterative approach and find ultimately that for the sun we are extremely successful. I don't know whether this is still state of the art, but already a while ago, the run of our knowledge of the run of sound speed and hence temperature, etc., with depth for the sun is amazingly accurate because we know it to better than 1 per mil. That's amazing. I find that still amazing. Okay? But it's gas dynamics. There's no magnetic field involved. It's 1D. It's ignoring the fact that the sun is sitting there and doing meridional rotation, etc. And the basic equilibrium here is inward gravity balanced by outward pressure gradients. Okay? Of course, that's all you need for your first star to be formed. Suppose I want to do the same thing, but now in an accretion disk, okay? Right, in an accretion disk, what is my basic equilibrium? Something completely different, right? I have here a Keplerian accretion disk. A Keplerian accretion disk is something that at every radius, the centrifugal force is balanced by the inward gravity, okay? And so I now have flow, and so I can ask myself, how does differential rotation change the dynamics and the spectral thing? And what drives then the accretion? Suppose I take this as an equilibrium and I want to quantify the stability. Why can't I do that? Of course I can do that. The point is that accretion disk physics, well, I challenge you, go to any paper in the literature that talks about, for instance, simulations of accretion disk, and you will find at least once the word magnetorotational instability. At least once. So, why? Because it has become common to argue the following. Well, we actually have very large accretion rates that are observationally established. If you take the gas dynamic conditions that we infer for these things, and we go to textbook viscosity prescriptions, then you will find corresponding accretion rates due to viscosity that are way too low to match with observations. So you have to have turbulence that enhances the viscosity to anomalous of effective things, and that turbulence must must arise from, well, you have an equilibrium which is somehow unstable and has a root for instability. So, if you have turbulence, what is the root, the basic reason for this to be turbulent? Well, if you have a differentially rotating system, okay, then standard gas dynamic textbooks will tell you that there is something known as the Rayleigh criterion, where if you have the specific angular momentum, so just the product of radius with the azimuthal velocity at that radius, if you have that sort of decreasing for increasing radius, then that situation is unstable to this Rayleigh criterion. It's just, that's what the Rayleigh criterion says, okay? And that is then a linear route to instability. Now, Keplerian rotation profiles, which obey this thing, actually are stable to the Rayleigh criterion. So we cannot argue from gas dynamics alone. So, it has come about that this magnetorotational instability is sort of the answer for why it is unstable, because if you have a weak magnetic field, then actually now you have a route to instability that, well, was already pointed out by Velikov, also Chandrasekhar, and then reinstigated and put into the context of accretion disk physics by Bulbis and Hawley in 91, and has become known under, well, the Bulbis and Hawley or the magnetorotational instability. And here is sort of a sketch of what we are, what you can, well, sort of understand why this is. Okay, so I have here a radial run, and my central object is further out there, okay? And then I have a magnetic field, okay? That I have here a field line drawn, and then my direction of Keplerian rotation is around this way. And magnetic field has this tendency of enforcing things to co-rotate, all right? So if I have, let's say, a weak magnetic field, so that I can argue when it's useful that, you know, magnetic field does things but don't really matter dynamically. Well, I displace this inwards, then this thing because of the magnetic field, will have the same rotational speed as these guys here, okay? Now, as a run of radius, of course, rotation is just at the right value needed to balance gravity. That's the whole essence of, Keplerian rotation. So if now this guy here, which was originally rotating here and is still rotating at this speed, now all of a sudden it's rotating slower than its immediate neighbors, slightly above and below this displaced field line. So now all of a sudden gravity can win it from centrifugal and it will run away. Okay? And this is one way of sort of, schematically explaining why a paramagnetic field could introduce, together with a radially varying velocity profile, a new route to instability, the magnetorotational instability. Now, suppose you're a seismologist and you would like to know, is that the only way for becoming unstable? It already works in axisymmetry, okay? So where, you have, of course, in this figure here, you have rotation in this azimuthal direction perpendicular to this plane, but you don't need any variation in that direction. You can do even numerical simulation or just analysis in a 2.5-dimensional configuration where the half dimension means that everything in this azimuthal variation is just, invariant. But it does explain the onset of turbulence in weakly magnetized electricians. But, occasionally we argue about equipartition magnetic fields. So what about that? And then, from the MHD spectroscopy point of view, I told you that in a uniform plasma, we have these nice diagrams which tell us the phase and the group speeds for slow, alphane, and fast. So where does this instability fit in? And what does rotation add to the spectrum? That's a question that is still not answered, and it's a whole open research field as far as I'm concerned. And I'll tell you what we know. And this goes back to theory written down before I was born. Okay? In 1960, Freeman and Rothenberg have written down the equation of motion governing the Lagrangian displacement of a fluid element by doing, what I told you should do if you want to quantify the waves and instabilities around a given configuration. You take your full set of equations, you write everything as this time-independent equilibrium plus a perturbation, and it is possible for MHD to combine all that to this governing equation for the Lagrangian displacement of a fluid element, irrespective of the dimensionality of the background equilibrium. 1D, 2D, 3D, with flow, with gravity, everything included, it's governed by this. This is the Freeman-Rothenberg equation. And I hope that more people start to use it. Because this is basically then quantifying, what is all in here. These are then the linearized forces, right? So linearized total pressure is here. This is linearized Lorentz force. Gravity is taken into account. All effects due to shear flow is all here. And this is then about an exact stationary gravitating magnetized spectrum. And then you can use it, right? You can use it. So here, the temporal variation is still not prescribed, and it's still full three-dimensional. But you can, for instance, insist on e to the I omega t. And for instance, this thing here, without all the velocity, without gravity, uniform magnetic field, etc., gives you the diagrams that I was, helping you to remember. If you go to a static background, okay, and that's where the knowledge of this field has, I think, arisen, then quite a bit of things drop out. Static field, so no velocity, so this part drops out, and this here is just the force operator. This part drops out, so you just have rho second derivative with respect to time of this Lagrangian displacement given by this piece here, which I now call force operator. And it turns out ideal MHD is also mathematically a beautiful theory, because this force operator in the Hilbert space of all allowed eigenfunctions that have a finite energy. So now we're talking in Hilbert spaces, and I don't know how many mathematicians get excited about that, but this operator is self-adjoint, and that means that integrated and dotted with the eigenfunction, okay, so psi. If I go to a Fourier analysis for the temporal dependence, okay, I am looking for eigenfrequencies and eigenfunctions, pairs of solutions. And this is saying that the force operator is self-adjoint, but the fact that it's self-adjoint means that the only thing that I can get out of this omega squared is a real value. Okay? That's mathematics for you. And then that means that omega squared, it's not because I write omega squared that it has to be positive. It can be positive or negative. And if it happens to be positive, then due to the e to the minus I omega t, it's just a wave that will have a certain frequency. If it's negative, it's an instability. And that means that actually it will cause a runaway instability. So if I do linearize the MHD equations about the uniform static state, I actually get a special case of this, and I showed that already. I get the three solutions, my branches, for the fast, the alphane, and the slow. And this was, I remind you, for a case where I had a uniform plasma, so uniform pressure, uniform density, unidirectional magnetic fields, and then perpendicular in that, so my directional field is horizontal, and then I say, okay, everything has to fit between, say, the bottom and the top of this room. Then I have boundary conditions, and so everything has to fit with a finite amount of wavelengths in that direction. And so that means that these continuous curves will go into a sequence of fast, infinitely degenerate alphane and slow modes accumulating to a predetermined frequency. Okay? And homogeneous plasma, slow, alphane, fast plane waves, and it's stable. We know that. The essential part of this spectrum is the fact that there is a possibility to accumulate with modes to infinity in terms of omega squared. That's part of the essential spectrum. There is alphane frequencies and there are slope frequencies. And alphane, slow and fast, which you know, if you know the equilibrium properties and the wave numbers, they form what is mathematically known as the essential spectrum. Okay? So how does the picture change when inhomogeneity is introduced? Well, when inhomogeneity is introduced, it turns out that, well, this infinitely degenerate alphane thing becomes now a continuous part of modes that is known as the continuous spectrum of alphane. Similarly for the slow. And yeah, what is continuous spectrums? Well, go back to quantum theory. You know, in quantum theory, we also have Hilbert spaces. We also have self-adjoint operators. And here, well, sort of the typical picture for the electron energy states in a hydrogen atom. We know that there are bound states corresponding to electrons sitting on nice orbits. And then when it has enough energy, it has a continuous range of, well, this is the free electron state. Okay? This is continuous versus discrete with self-adjoint operators. there is a perfect analogy between magnetohydrodynamic theory for static plasmas and theory acquired in quantum settings, basically. And I don't have the time to tell you all about that, but in MHD, basically, we have the equation of motion, okay? We can turn it into an eigenvalue problem, and we can use that to quantify the spectrum and all the modes. And there is a clear analogy with, well, you can also turn it into quadratic forms, okay? These things I'm going to try and explain in a minute. The bottom line is that the picture that I had before, okay, in a homogeneous plasma, I was showing you that if I vary my horizontal wave number and I have a certain configuration, I have here the fast modes, the alphane, and the slow modes. And if I quantify my wave number here, I get discrete values. And so on my omega squared axis, I get my fast modes accumulating towards infinity, a point that is the alphane, which is infinitely degenerate, and my slow sequence going towards the slow thing. Now I'm saying inhomogeneity changes this into a continuous range, and it does so. And here it changes the schematic picture. I don't put it vertically but horizontally, but that's not the real thing. I have here the fast accumulation point. These are the P modes. I have here the alphane range, which can also act as a possibility to collect discrete modes governed by gravity. And I have similarly modes that can be collected to the slow, also governed by gravity, and those connect to the G modes, right? And then I have here, well, the possibility for Rayleigh-Taylor instabilities introduced by gravity. So I start to make connection with the PG mode picture from the helioseismology. This is still in a non-moving configuration, okay? In this non-moving configuration, I can even, okay, well, I can make quantifications of these P and G modes for different wavelengths, okay, and hence build up my theoretical P-mode-G-mode diagrams, all right? That is what is done here for, in fact, a magnetized but gravitationally stratified layer between, well, a bottom and a top. And this is analytically reproducible, and that is, of course, what is done also in helioseismology, where you don't have the field, but you just have pressure and gravity, and it sets up a P and G mode structure. And then, in fact, here the run of the configuration is such that there are no continua. The hair in the soup has been taken away, okay? If you change the parameters that govern this setup, okay? For instance, if you go to a case where magnetic field is more important, then, well, you can also check regimes where all of a sudden you come into Parker instability regimes. What is the Parker instability? It is an instability that actually relates to, well, buoyancy essentially operating along, you know, deformed magnetic field lines. Well, Rayleigh-Taylor is related to gravity. Interchanges is another way of modes that, well, also have to do with the field. And everything depends on the orientation of the wave vector with respect to the magnetic field. So here I have my theoretical diagram of P modes, G alphane, and I should point out G slow here. There are also G slow modes. I can change this is at a case typical for solar, so ignore magnetic fields. Take magnetic fields serious, beta equal 1. I can show you fast, alphane, and slow modes here, all right? They become more visible, and still the hair is out of the soup. There is no continuous range of the spectrum here because it's being collapsed to constant alphane and south speed. Anyway, I have already a possibility for turning this sequence of modes that connect to the slow. If I zoom in on the behavior near the origin, I actually have the most global modes becoming possibly unstable at a finite angle between the wave vector and the magnetic fields. Okay? If I vary the angle with respect to the magnetic field at this field strength, I can actually do this. So here I'm now varying the angle from 0, so aligned with the magnetic field, to perpendicular to the magnetic field, to, well, okay, anti-aligned with the magnetic field. And then again, I'm now only interested in slow and alphane, and then my P modes, okay, they're up there. But if I'm perfectly aligned, these modes that were in here at angle pi over 4 actually match up to the Parker instability, okay? And those are instabilities that are manifest themselves when the wave vector is parallel with the magnetic field. But if it's not parallel, then, I mean, that's not what Parker discussed, so it's probably quasi-Parker, right? But then if you vary the angle, then you see that not just the most unstable modes, but the whole range of modes becomes unstable. And that is from the tokamak experience and literature, this is quasi-interchange and interchange modes. And so you can build this whole picture and connect to every different, instability that you can find in the literature. All of that was static, no flow in the configuration. So what happens in the stationary case? In the stationary case, in the static case, I had omega squared psi is the force operator. Well, I still have a generalized force operator, but now I have to take into account all this mess due to shear flow. And the fact that there is a Doppler shift, okay? So these are now just another way of writing this Freeman-Rotenberg equation with splitting off and collecting bits and pieces in certain operators. The main point to note is while static is governed by one self-adjoint operator, stationary case is governed by two self-adjoint operators, which are the generalized force operator and this, what we call the Doppler-Coriolis operator. And because the fact that now not only omega squared appears, but also omega in combination with this Doppler-Coriolis, you now have possibility to go into the complex plane, not only through the origin, but any which way you want, okay? So it becomes possible to have intrinsically complex eigenvalues, not just stable waves on the horizontal frequency axis or instabilities on the imaginary axis, but overstable modes, and this is the root for Kelvin-Hell modes, all right? So, but still, these normal modes, they obey the spectral equation, which I have just formulated. And it's now a quadratic eigenvalue problem supplemented with boundary conditions governed by two self-adjoint operators. Okay? That's in a nutshell. So this is what I'm trying to say, that while before you had here the complex frequency plane, all the stable waves, the P modes, the G modes, except perhaps the Rayleigh-Taylor instabilities would, you know, all lie here on the stable frequency axis, and you would have one route to instability through the origin. Now, we can go into the plane every way which we want. However, it's not as bad because we have two self-adjoint operators, okay? And if we do and use that, then you can actually do more. And you can start putting order into the complex plane. Okay? Just like you put order into the static case, because P modes form a nice countable sequence of Sturmian behavior. You know, and the G modes and the other, it's Sturmian and anti-Sturmian behavior, like you learn in, well, whichever course you take it. So now we have here, if you have an eigenvalue, eigenvector pair known, suppose you know a case, then it has to obey this relation, which is just this Freeman-Rothenberg relation written now with the G and the U operators, okay? You can introduce, again, well, you take the complex conjugate of these eigenfunctions. Remember, because we go into Fourier representation with e to the I omega t, we have complex eigenfunctions, but okay. We can take the product of that. We get, well, a quadratic formulation of that just by dotting with the complex conjugate, and integrating is this thing here. Okay, and this is, well, what are we doing? We are integrating over the volume something that changes with the volume coordinates. So that's a number, all right? So we have this thing here that has to hold for eigenvalue, eigenvector pairs. And in fact, for actual eigenvalues, you can argue that this relation will hold, and that the quadratic forms here, that here appear are real. Okay. So how now do we locate where the complex plane is very big? So where do we find the eigenvalues? Well, there is a way to find them by using this background theory, okay? You are actually faced with solving the linearized MHD equations, which if you have a one-dimensional varying equilibrium actually are just a set of ordinary differential equations. If you have a two-dimensional, a set of PDEs, but it's possible to actually solve these things nowadays. But for solving ODEs of PDEs, you not only have to integrate, but also provide boundary conditions, right? And this is if it's 1D, you have two boundaries, you have a second-order PDE. So typically, what you can do, you take a random complex value, you obey one boundary condition, and then you integrate. Use your favorite ODE solver, and then you arrive at the other step, other thing. Typically, you won't obey the second boundary condition, telling you that, well, you can only obey it if you have actually found an eigenvalue, eigenvector pair. But you can quantify the values there. And eigenvalues are those that actually satisfy all boundary conditions. So from this point of view, where will the eigenvalues be located? Well, if we raster up our complex plane and we do an embarrassingly parallel ODE integrator from everywhere at the same time, it's trivial nowadays, you can then quantify what are the values and make contour plots of there where one of these quadratic terms becomes truly real. Then, you know, on that curve in the complex plane, and only on those curves, my eigenvalues will be situated. You can call those curves the solution paths. In order to locate, so now, that's already a big step. Huh? First, you have to look in the whole complex plane. That's pretty big. Now you have located them on curves. It's still big, but it's much smaller. And now, if you were to be able to identify yet another curve on which they are sure to lie, then you find them on the intercepts. And the intercepts, well, another way to look at this, well, you also have to obey, well, the second boundary condition. Well, in fact, knowing what you have obtained at this extra boundary, at the outer boundary where you have reached, well, there you can quantify things like perturbation, well, displacement over total pressure perturbation. That's something that relates to an impedance. the zero value is given corresponding to the boundary condition. So actually, you can plot this for all your things, and then you also find curves. And the point is that then you have two sets of curves, and so you can locate them in the complex plane. This is the same thing. And now the main point is that, okay, I'm no longer going to draw these things with omega squared, but I'm going to draw these things with the full omega. So now the point is that we have, as I was also saying in the wave categorization, we have forward and backward Doppler-shifted eigenfrequencies. And so in the hydrodynamic case, okay, you would have your p modes going both to the plus and the minus infinity. You would have a continuum that is known as the flow continuum that has also been discovered in the 1960s by Case. And then you have the G modes accumulating to this flow continuum. The MHD picture is much more complex. We now have this no longer a flow continuum, but 4 ranges of continua, the backward and forward shifted alphane and slow continua, and then all the possibilities to accumulate with discrete modes towards infinity and towards any of these continua. And then, in addition, the possibilities to go into the complex plane due to shear flow effects. Okay, that being said, I have only 5 minutes. So let's take a force balance for an disk that has all of the ingredients. Well, Keplerian rotation, magnetic fields, pressure gradients, and that is representing then the variation with radius in the midplane of an accretion disk. Okay? And then do this analysis. Well, here is a plot of the complex plane. And here are actually my fast modes. Okay? Here are modes, well, here zoomed in actually are my range for my overlapping, because it's a very weak magnetic field, alphane and slow continuous ranges. And then there are these modes that seem to lie on the imaginary axis, but actually they don't exactly, because there's a helical magnetic field, and those are the magnetorotational instabilities. And everything is organized about the combination of backward and forward fast alphane and slow continua. And the magnetorotational instability is somehow one of these possibilities to accumulate towards the slow stop spectrum. And this is what I was telling, that if I take this configuration here, okay, I have these MRIs, how can I be sure that they are the right eigenmodes? Well, I can plot these two sets of curves that I was talking about and find that they are indeed, well, okay, at the intersections of, well, these two, contours that I was discussing just a while ago. And if I change my parameters, this is what I've done here, I can go to locate the eigenvalues. These were axisymmetric modes. These are non-axisymmetric modes, and I find eigenvalues like this. And now, of course, I can go wild and do quantifications of where is my spectrum if I change my parameters, okay? So my parameters are what is the strength of the magnetic fields, what is the aspect ratio of the disk, what is the mode numbers for my waves, how helical is my magnetic field configuration. And here at the bottom, I always now show the complex plane, okay, the eigenfrequency plane. These are fast modes. And here at the top, I show now, as a function of the radius, the analytically known location for my, in this case, overlapping alphane and slow continua under these parameters. In this case, it's stable. All right? If I change my wave number, my continua lie here, and I see modes coming out of the origin. It's unstable. Those are the MRI modes. Okay? And I can follow this for changing wave numbers, okay? And you can see how now you have this sequence of modes coming out of the origin. That is the MRI mode. But you can see if I change my parameter, it's actually a countable sequence, okay? And you can see the modes as I change my wave number being peeled off and then join the sequence as they should, you know, along the stable part of the axis, okay? And so here I go to a more stable configuration. And in this way, I can plot my most unstable mode as a function of wave number. Okay, and so I can quantify these things, but I actually know much more than this. I know the full spectrum. I can also do this for non-axisymmetric modes, and I mean, this is just something that we are starting to do, so it's kind of fun to make these kind of quantifications here. Okay, plasma beta is 100. I'm now looking at non-axisymmetric modes, and you can see in the top panel that actually, because of the plasma beta being so high, the forward and the backward alphane slow continua are separating more and more as I increase my wave number k. And you can see how some intricate modes, which I would not necessarily instantly label as magnetorotational, but as true eigenmodes of the MHD spectrum, pop up and become more unstable as k is increased. Of course, you can go to stronger fields. Okay, there is nothing that stops you. And then plot things like, again, growth rates versus wave number for just different configurations. And so here is yet another one of these parameter studies where I'm just making more beautiful paths in the complex plane where I find my eigenmodes. And again, above the imagery 0, those are my instabilities. Below are stable modes. And the, well, those are damped modes, excuse me. And the stable modes, so the you know, the helioseismologists are looking at these, right? So here we have now, well, okay, modes of which I can not yet say much more, except that they are there. And with that, I probably should stop. And I'm going to skip all this. And say that these quantifications were for a one-dimensional equilibrium with everything in it. Azimuthal, shear flow, magnetic field as a function of radius, pressure, gradients. But it still was one-dimensional. This Freeman-Rothenberg also works for two-dimensional. But then you have to first construct an actual equilibrium, which is two-dimensional. The part I skipped is telling you that there is already quite some work done on first obtaining two-dimensional equilibria for thick accretion disks and quantifying the modes. And then it becomes really intricate because now these continuous spectra can show avoided crossings and gaps and form the location for gap modes and form all kinds of new routes for even unstable continuum modes, which I would really not always call magnetorotational instability. So my main message to you is, if you write a paper and you say accretion disks and it's unstable, don't instantly write magnetorotational instability, because there's much more to the story than magnetorotational instabilities with weak fields. Okay? And I can give you examples of modes that are really driven by completely different mechanisms. I'm Belgian, so it's like saying that every Belgian beer is Stella. Okay? That's an insult to every other beer but Stella. Okay? So that is what I wanted to stress. I haven't yet started about non-ideal effects, okay? And in fact, by going to this Freeman-Rothenberg description, I have thrown away one of the 7 modes. I told you yesterday, magnetohydrodynamics has 7 modes: forward and backward, slow, alphane, fast, and the entropy. The entropy is not in the Freeman-Rothenberg description because in ideal MHD, it's completely boring. But if you add non-adiabatic effects, then you form a route for thermal instabilities, okay? And of course, there's a lot of physics associated with that. If you add self-gravity, which I haven't, then you have genes instability. But everything is nice and, well, still to be looked at. And of course, you can follow all this up with global nonlinear simulations, where you set up configurations which you have diagnosed exactly from the spectral point of view, so you know which and why is there an instability, and does it lead to turbulence, accretion rates, and field amplifications. This is a snapshot of a modern global accretion disk configuration simulation, where you see that in this snapshot, which quantifies the plasma beta throughout the disk, from the initial condition, it has actually, you know, of course, in this paper, it's called magnetorotational instability. It probably is in some way, but I'm saying there is more. And then there is, well, ultimately, in this nonlinear saturated state, there is efficient angular momentum transport, and you have regions where the field is far from weak, and so where you can hardly claim that there locally there are magnetorotational instabilities active. Now, I also don't, I mean, I'm not able to instantly tell you what is active where, but I'm saying that, you know, it's interesting to ask the question, where does it come from? And with that, I have told what I wanted to say. Thank you.